In our everyday experience, the world is 100% measurable, deterministic, and independent of the observer. But in the quantum universe, this isn't necessarily the case. A radioactive atom that remains unobserved will exist in a superposition of decayed and undecayed states until that critical measurement is made. The three valence quarks making up your proton may all have a definitive color anytime you measure them, but exactly what color you observe is guaranteed to not be constant over time. And if you shoot many electrons, one at a time, through a double slit and don't measure which slit it goes through, the pattern you see will indicate that each electron went through both slits simultaneously. This difference between classical and quantum systems has resulted in both scientific and technological revolutions. One field that's only now emerging is quantum computing, carrying the fascinating notion of quantum supremacy along with it, but also spawning a large series of dubious claims and misinformation. Here's an explainer about quantum supremacy and the current state of quantum computers to help you separate fact from fiction. Let's start with an idea you're probably familiar with: the notion of an everyday computer, also known as a classical computer. Although calculating machines and devices had been around for a long time, well prior to the 20th century, it was Alan Turing who gave us the modern idea of a classical computer in the form of what's now known as a Turing machine. The simple version of a Turing machine is that you can encode any type of information you like into bits. Binary components that, for example, could be represented by zeros and ones. You can then apply a series of successive operations to those bits. Operations such as and, or, not, and many more, in the proper order to perform any sort of arbitrary computation that you had in mind. Some of those computations will be easy to encode and easy for the computer to perform. They require only a small number of bits, a small number of operations, and a very short time to compute them all. Others will be hard, difficult to code, computationally expensive for the computer to perform, and potentially requiring large numbers of bits, large numbers of operations, and long computing times. Regardless of your desired computation, however, if you can design an algorithm or method for successfully performing any computational task, you can program it into a classical computer. Eventually, given enough time, your computer will finish the program and deliver you the results. However, there's a fundamental difference between this type of classical computer that works exclusively with classical bits and classical operations and a quantum computer, which was purely a theoretical construct for many decades. Instead of regular bits, which are always in a state that's known to be 0 or 1 with no exceptions, regardless of how or even whether you measure them or not, quantum computers use what are known as qubits, the quantum analog of bits. While qubits can take on the same values that classical bits can take on, 0 or 1 in this case, they can also exist in an intermediate state that's a superposition of 0 and 1 simultaneously. They can be partway between fully 100% 0 and fully 100% 1 in any amount that sums to 100% in total. The amount of 0 and the amount of 1 that a qubit possesses can change both as a result of operations performed on the qubit and also due to simple time evolution. But when you actually go to make that critical measurement of a qubit and you ask it, "What quantum state are you actually in?" you'll always see either a 0 or a 1 in your measuring device. You'll never see that in-between value directly, even though you can infer that, based on the qubit's effects on the overall outcome of the system, it must have simultaneously been a mix of 0 and 1 while the computation was taking place. Quantum supremacy is the point at which a quantum computer can perform a calculation that is practically impossible for a classical computer to achieve in any reasonable time frame. This milestone, however, is not just about raw computational power. It represents a paradigm shift in our approach to solving complex problems. In 2019, Google claimed to have achieved quantum supremacy with its Sycamore processor, solving a specific problem in 200 seconds that would have taken the world's fastest supercomputer approximately 10,000 years. Critics argued that the problem solved was highly specialized and not particularly useful outside of proving the point. Nevertheless, it was a significant step forward, showcasing the potential of quantum computing. But quantum supremacy is just one part of the equation. As we delve deeper into the quantum realm, it's crucial to understand the current limitations that define the power of quantum computing. Two primary factors set these boundaries. The number of superconducting qubits a quantum computer can control simultaneously, and the efficacy of quantum error correction. Quantum circuits, by their nature, are prone to errors. The longer a computation takes, and the more qubits involved, the higher the likelihood of errors. This makes achieving quantum supremacy, or the more ambitious quantum advantage, a formidable challenge. To reach these milestones, researchers must design computational problems that require a minimal number of qubits and can be solved within a short time frame relative to the coherence time of the qubits. In 2019, Google made headlines by demonstrating quantum supremacy with its Sycamore processor. They solved a problem tailored to be extremely difficult for classical computers, but manageable for a quantum computer. Critics, however, pointed out that this problem had no real-world application and was specifically designed to showcase the computational prowess of quantum systems. Despite this milestone, we are still far from solving practical problems faster on quantum computers than classical ones. For instance, consider a 20-digit semi-prime number. No current quantum computer can solve this, while an ordinary laptop can do so in milliseconds. This stark contrast highlights the gap we need to bridge. However, incremental advancements are being made. As we move toward a new era of quantum computing, it's essential to temper our expectations with a realistic understanding of its capabilities. The ultimate goal of quantum computers, at least in the short term, is to simulate quantum systems that are computationally expensive to simulate classically. This is where the first practical application of quantum advantage is expected to arise. Whether the field of material science, high-energy physics, or quantum chemistry will be the first to reap the practical benefits of quantum computers is anyone's guess. With the anticipated increase in the number of superconducting qubits, longer coherence times, and superior error correction techniques, the computational power of quantum computers is steadily increasing. Eventually, we will solve the first practical, real-world problems that are computationally expensive for classical computers, quickly and efficiently, with quantum computers. However, it's crucial to recognize that quantum computers will not replace classical computers for most applications. Achieving quantum supremacy does not mean that useful quantum computing has already arrived. Instead, our future will likely be a computationally hybrid one, where classical computers handle most of our computational needs, augmented by quantum computers in areas where quantum advantage can be achieved. Just as classical theories from Newton, Maxwell, and Einstein cannot explain all physical phenomena, there are many computational problems awaiting the development of superior quantum computers. With quantum supremacy already achieved and the more practical quantum advantage on its way, we have much to hope for in the realm of quantum computing. Yet we must also be cautious of the hype and the many false claims that may arise. Stay informed, stay critical, and continue to explore the evolving landscape of technology.